one of the things that I always encourage you to do with any gas law problem, at least any Boyles, Charles, Gay-Lussac's, Avogadro's, even try to do it in a combined gas law, is I encourage you to, try to figure out what should happen to your variable, the one you're solving for, before it happens to it. So, ladies and gentlemen, for us to be able to do that, we need to identify some things. So, number one, 105.3 is a pressure. There is no new pressure. That is what we are solving for. So that means in this problem, we are going to be solving this problem for pressure. P2 is what we are going to be solving for. Okay? For us to be able to do that, ladies and gentlemen, I have to have two temperatures. Well, I've got 15.8 degrees Celsius and I've got this 45.6. But what do we have to be careful with in this problem with the 45.6? It was raised that much. Not it is going to that temperature. It was raised by that temperature, which means we're going to have to add it to our original temperature. Okay? So you can't just look at the numbers. I also need volumes here. So I've got a volume of 698 milliliter and a volume of 421. Okay, so now, what is happening to the temperature in this problem? Up or down? Up. That should cause the pressure to want to go what direction? Up. They are in a direct relationship. Now, I've also got a volume. Volume is doing what in this problem? Volume is going down. What should that cause pressure to do? So ultimately in this problem, what's got to happen to our pressure? It has to go up. Pressure cannot go any other direction. If these two arrows are not pointing in the same direction, we can't tell what's going to happen to it. But when they are, we could tell what's going to happen to it, ladies and gentlemen. So what that means is that now that I'm ready to do my calculation, now I know final answer pressure better be bigger than 105.3 kPa. So now I could take and I could put everything into my formula. Please remember, we need to convert temperature from Celsius into Kelvin, which means I'm going to take 15.8, add 273, get 288.8. I'm going to add 15.8 and the 45.6 because it said it was raised by that. And then I'm going to add 273 to it. That gave me 334.6. Everything goes into our formula now. The pressure times the volume over the temperature is equal to the pressure times the volume over the temperature. Now, because you have something on the top and the bottom here, my suggestion to you is to put this all into one line using cross products are equal. But again, you don't have to as long as you do the correct math. Ultimately, I want to get P2 alone. So ultimately, I'm going to take this side times 334.6, and what I do to one side, I'm going to do to the other. But I also have to divide this side by 421 milliliters. So you can put it all on one line. You can arrange it from there. Choice is up to you. I'm going to get P2 alone by dividing this side by 421 milliliters and 288.8 Kelvin. What I do to one side, have to do to the other. Now, you are going to take these three numbers and divide them by these two. This is where you have to be careful with your calculator and your math. Sophia.
You did the Kelvin math, because a 0.8 plus 0.6 should not equal 0.6. Because it's 0.4.
Okay, thank you. So 334.4?
Yeah.
Okay.
Oh my God, this is embarrassing.
It's okay. I'm used to you guys making mistakes.
I did food after this.
Oh, you have a letter. person.
What do you think?
I don't know. I'm so-
Okay, there we go. So let's go back to it, ladies and gentlemen. Okay, so to get P2 alone, ladies and gentlemen, I'm going to divide both sides by 421 milliliters and 288.8 Kelvin. Kelvin and Kelvin cancel. Milliliters and milliliters cancel. What unit am I going to be left with?
KPI.
Good. Now, again, you are dividing these three numbers by these two. You have to figure out how you want to put this into your calculator. When I put it into my calculator, I will multiply these three numbers. I will hit divided by, and I will put these two numbers in parentheses on the bottom, multiplying them together.
Like
If you do,
Sorry.
well, you do not need parentheses around each of these numbers. The reason I do it is to show you this is one term.
Well, if you do that, it should multiply, right?
If you do it this way, the way I have it down here, it will not.
Oh.
It will not multiply them together before you divide it. It will divide by this one and then multiply by this.
Okay.
You will end up way
That's why I
about
was
900
thinking
times
about
off.
this
Okay?
yesterday.
So these numbers need to go in parentheses on the bottom. You do not have to put 421 in parentheses in your calculator times 288.8 in parentheses in your calculator. What you need to do is this. This is the way I would enter it into my calculator. You put it in like that, you will get the right answer. You put it in another way, depending on your calculator, you may or may not get the right answer. Okay? Now again, my suggestion to you is as we're doing these, I would practice by grabbing a calculator and doing it. But if you don't want to, I guess you'll find out on the test if you've been doing it right or wrong. Pressure comes out to be 202 kPa, ladies and gentlemen. 202.269 if I did my math correctly, which is questionable today. All right? Round this to 3 sig figs because every one of our numbers up above except for the 105.3 kPa had 3 sig figs. So again, sig figs are easy in these problems because we are doing multiplication and division with them. Whatever is the smallest amount of sig figs up above, that is the number of sig figs that your answer goes into. Questions?
How many units do we have?
Well, what unit are we on?
6.
Good. And how many units do we have?
8.
Good. Now let's
Oh,
do
really?
so. Oh, wait. Take a calculator and take 8 minus 6. Questions? Okay. So, sulfur trifluoride gas is under the following conditions. Pressure, 0.986 atmospheres. Temperature, 31.6 degrees Celsius. Volume, 2.36 liters. What is if the pressure is changed to 1.31 atmospheres and the volume becomes 1,236 milliliters? What will the new gas's temperature be in Celsius? That doesn't mean we do our calculations in Celsius. That means at the end, we do what?
Convert it back.
Convert it back. Okay? We convert it back. All right. Excellent, ladies and gentlemen. So let's take a look at this. All right. Here's the first question. We are finding a new temperature. That's what we are solving for. We are going to change the pressure.
Now, why would you do that?
Why would I do what?
The liters and then the milliliters.
Why not?
It just makes it harder for us.
Really? Really? You have trouble dividing by 1,000? You have trouble sliding a decimal 3 points,
Will you
3
ever
places.
give us like the pressure different ones that we have?
Oh
to
yeah,
do?
definitely.
When?
Probably on the test.
Oh, on the test.
So Well, it's not this week, Friday.
Next week, Friday.
Okay, let's go with that. Good idea.
What?
We'll do that.
Is it actually?
Sophia.
Wait, no, how about June 2nd?
So, what happened to pressure, ladies and gentlemen, in this problem?
What?
What happened to pressure in this problem?
It's changed.
How?
It went up.
Went up. What's that going to do for temperature?
Go up.
Should make it go up. Doesn't mean it is going to, but it should make it go up. All right, what happens to volume here?
It goes down.
Volume goes down. What should that make temperature do?
Go up. Go down.
Down.
Stay the same. What? I don't know.
The relationship between volume and temperature is a direct relationship. If volume goes down, temperature is going to go down. So, the only way for us to figure out what happens to temperature is to actually do the problem, ladies and gentlemen. We cannot make a prediction. So, let's take and do the problem.
Can we ever change all four? Like things like amount, pressure, temperature, and volume? Have they ever changed all four?
You know what? Sure, we could.
Are you gonna make us?
I don't know, we'll see.
Are you gonna tell us on the test what law we're using for each problem when we have to figure that
Oh my god.
That's funny. That is the funniest thing you have said to me. Yes, of course I'm going to. Please use Boyle's law on this problem.
This is why people don't ask questions.
Right.
Sorry, that was very inconsiderate of me. No, I will not be giving you which law to use. And by the way, by the time we get to the test, you've got about 7 different formulas you'll be able to use.
What?
Ew. You're so nice.
Would there be one that works on every single one?
No, that's why you have 7 different ones. Okay,
Why?
so let's convert Why? Because there's that much about gases. So let's convert our volume of gas into liters so that we're in the same unit. By the way, if you want, you could have taken the liters and converted it into milliliters. It doesn't matter which unit you use as long as you're using the same unit. So, setting it up, T2 is what we're solving for. Here's our new pressure. Here's our new volume in the same units now. Take and put everything on one line, ladies and gentlemen. We're going to divide this side by 0.986 times 2.36. What we do to one side, we do to the other. Atmosphere and atmospheres cancel. Liters and liters cancel when this is brought down to be under this side. Only unit left we are left with is Kelvin, ladies and gentlemen. We are left with Kelvin. Okay? Do the math. We get 211.9 Kelvin. To get into Celsius, we subtract 273, giving us a negative temperature of 61.1 degrees Celsius. I thought you couldn't have a negative temperature.
When it's Celsius, you can.
When it's Celsius, you can. When it's Kelvin, you cannot. Questions?
What's the next unit?
Why don't we worry about this one first? So, questions? By the way, what actually happened to our temperature here? What happened to our temperature here?
It went down.
Went down. What caused that?
The volume.
What?
The volume.
Volume caused it. Why? Pressure was trying to send it what direction?
Up.
Volume was trying to send it.
Down.
Volume wins.
Why?
Volume won.
Like, does it win every time?
No.
Just in that equation?
Because if you look at this change here, this is about adding 30%. About. This is going down almost half. Going down half is a bigger change than increasing by 30%. Volume wins. Somebody asked me yesterday, I don't remember who was this class or other, is there a hierarchy for which one Winds normally, no. It just depends on how big the change is. Jennifer, can you wait till I'm done and give you time to work on things? Thank you. Okay. All right. Really? That's it? Huh. There it is, all in one place for you, ladies and gentlemen. All in one place.
Except for combined gases, which is on the next slide.
Correct.
Come on.
So, this is the 4 gas laws that involve only 2 variables, ladies and gentlemen. That tells you what the variables are. That tells you what the constants are. That tells you what the relationship is. By the way, what do you notice is special about Boyle's law? It is the only one that is inverse. It is the only one that is inverse. In every formula that has pressure, it is on the top. In every formula that has volume, it is on the top. In every formula that has temperature, it is on the bottom. And in every formula that has the amount of gas, it is on the bottom. Why? For consistency, ladies and gentlemen. For consistency. You could, if you wanted, you could literally flip these formulas upside down. It doesn't matter. It is a proportion. This fraction is equal to this fraction. But you need to make sure that whatever unit is on the top on one side, because they are equal, it has to be on the top on the other. This is not unit cancellation. This is 2 proportions that are equal to each other. Okay? Anyone need more time with this slide? And then yes, as Ava said, here is combined gas laws. You'll notice that the relationship says it's inverse and direct. Why? Because we go back to the original gas laws to figure out what the relationship is between pressure and volume, pressure and temp, volume and temp. Some are inverse, some are direct. That is your formula that you will use for it, ladies and gentlemen. And again, that one can take the place of Boyle's, Charles, and Gay-Lussac's. You have the last page in the first packet that I gave you, ladies and gentlemen. It has all combined gas law problems on it. Go to work. I'll be back later on to talk about ideal gas before we leave.